Here is an introduction to the Jovian planets to accompany Chapter 7 of the textbook Astronomy from Open Stax. So the Jovian planets, these are the gaseous and icy sort of giant planets in the outer solar system that we talked about, in the introduction to the solar system lecture. This lecture here is going to be kind of a whirlwind tour of properties of the Jovian planets. If this kind of stuff is your thing and you want to learn a lot more about it, you should take Astronomy 1001, which focuses on planets and moons of the solar system. When we talk about the Jovian planets, we not only have, Jupiter, Saturn, Uranus, Neptune, we also tend to consider objects in this outer reaches of the solar system. So we'll be talking about things that are further out, like the Kuiper belt and the OORT cloud and the stuff that populates them. The largest planet in our solar system and the largest Jovian planet is Jupiter, and this is the view from the South Pole in case it looks a little bit unfamiliar. It's huge. It's much larger than the Earth. It's 5 times the distance from the sun than the Earth is, and the days though are about half the length of ours. And one thing I want to mention before I forget is I have again the astrological symbols for these just because they're kind of fun that they exist. So it's very different, right? The Jovian planets are very different than the terrestrial planets. So we have a still substantial rocky core, but that's not the majority of the planet. On top of the rocky core, you have metallic hydrogen, a huge layer of that. You might wonder, how does that happen? Keep in mind that the pressures here are extreme, and so you can get phases of matter that are very hard to reproduce here on Earth. So a huge layer of metallic hydrogen. Then there's a layer of hydrogen that is a fluid layer, and I'm saying fluid because calling it a liquid or a gas doesn't make sense really. It's in a supercritical state, and so there's no distinction between a liquid and a gas at that point. And that's most of the rest of the atmosphere, and it rains helium and neon, so they condense and then rain down to these layers, which is kind of amazing. The atmosphere is extremely stormy, so the clouds are mostly made of ammonia. The winds, hundreds of kilometers. There's very powerful lightning storms, and you can see this is the Voyager probe footage from the 70s of the Voyager probe approaching Jupiter. You see these, wind patterns here and massive cyclones, much larger than the size of the Earth, that we know are sustained for a long time. So the famous one is this Great Red Spot, and it's at least 200 years old. So it's been observed for that long, and there's other cyclones that come and go. There is also a faint ring system of dust. It's not particularly prominent. It's relatively simple, but it is there. And Jupiter has a ton of moons, so there's at least 79 of them, but pretty much all of the mass is concentrated within these 4 moons that we call the Galilean moons. The Galilean moons are Io, Europa, Ganymede, and Callisto. Historically, they're extremely important because they're the first objects that were ever observed to be orbiting something other than the sun. And so that was obviously a big development for the history of astronomy. So Io, this is a rocky planet. It's extremely geologically active, so more than 400 active volcanoes. And the geology here is driven by tidal forces. So Io is stretched and compressed somewhat by Jupiter. It's relatively close to Jupiter, and by the gravitational forces from the other Galilean moons. And so that sort of stretching and compressing winds up driving geology on that planet. Europa, this is also rocky. It has a ice crust, and that's water ice. And we believe that there's a subsurface ocean of water lurking below there, and that's also going to be true for Ganymede and Callisto as well. Ganymede's huge. It's a very large moon, the largest in the solar system, and it's actually even larger in volume than Mercury. right? So it's technically it's bigger even than a planet. It's less massive because it's less dense. And then Callisto, it is the furthest of the Galilean moons from Jupiter. Because of that distance, there's no really the tidal forces are not significant, and so it has no geologic activity. It is thought to have the subsurface ocean, and what's neat about it is that because it's so far from Jupiter, it's far from its this region that's called the radiation belt, where basically energetic particles can be trapped in bombarded objects. We have a radiation belt around our Earth, so it's outside of that, so it's not bombarded by radiation there. We're extremely far from the sun, right? We're 5 Earth to sun distances, and so there's a relatively low radiation burden on the surface of Callisto. And so if you want to imagine a future scenario where we travel out in space and send astronauts, so far they've only been to the moon, there's planned missions to Mars. Imagine sending people out to Jupiter. This could be a possible base to land on and use as a home base for exploration of things in the area of Jupiter. Now, to be clear, that's a little bit sci-fi. That'll probably never happen in my lifetime, but it's at least plausible. So moving on, the next gas giant is Saturn. It's twice the distance from the sun as than Jupiter is. The days are about the same length. It is, much less massive. So about a third of the mass of Jupiter, relatively similar radius, and obviously has a very substantial ring system, as the most famous feature of Saturn. The interior structure is pretty similar to Jupiter, we think. Because we're now so far from the sun, Saturn radiates more energy, more heat than it receives from the sun. And that is energy and heat left over from its formation and due to some gravitational contraction, maybe some other more complicated things as well. But that's remarkable, right? That's how far we are from the sun, and you can place that in context by here's the Earth, right? It's that tiny little dot that you might think is a speck of dust on your computer screen. That's what you're looking at there. You're really, really far from the sun. The atmosphere is also extremely stormy. The winds here are incredibly high velocity, so 1,000 kilometers per hour. That's not quite the fastest in the solar system, but it's pretty fast. Another neat feature of the atmosphere of Saturn is on the North Pole, you have this hexagonal feature, which is kind of neat. So this isn't photoshopped or anything. That's real. And the reason for this isn't totally understood. There are competing theories, and most of them have to do with relatively complicated explanations involving fluid dynamics. But this structure has been reproduced with computer simulations, and so it's thought that basically complicated fluid dynamic effects are what cause that neat structure. And I should mention that excuse me, that Jupiter also has some neat polygons if you look close on its surface. A lot of moons here, so there's at least 82. If you check this number in a few years, it probably will have grown because moon, there could be really small ones, so people are discovering more kind of all the time. By far the most prominent is Titan, and what makes it significant is not only its size relative to all the other Saturnian moons, it's that it's the only other object in the solar system other than Earth that we know has a surface liquid. And it's water, but it's very ammonia rich. So this is NH3 if I remember. But yeah, it has surface water, which is kind of remarkable. And of course, it has a very prominent ring system. The rings are, by far the most substantial of any of the planets in our solar system. Quite a bit of mass, and it's mostly made up of water ice crystals that aren't terribly big, right? Up to a meter in size. More of them are probably more like the size of a basketball or something like that. And they're classified by different different letters to keep them straight, and you can see, there's obviously different features of these, and that's why they get the different classifications. Where they're located is, roughly 75,000 to 140,000 kilometers from the center of Saturn, and it's, relatively speaking, extremely thin. So you're mostly, for most of this disk, it's only a few kilometers thick. And a kilometer is, of course, a very far distance on Earth, but compared to the size of Saturn itself, this is an extremely thin disk. As you get further out, they get puffier, and you can get up to 1,000 kilometers, but for the most part, you're only a few kilometers thick. Now you're probably wondering, what are these gaps, right? Those are really interesting and neat. They're, for the most part, not actual gaps. They're just lower density regions, so there's still material there, but less dense. Some are true gaps. And they're basically caused by moons, and also by gravitational interactions with the moons, with the mass of the ring itself, and with Saturn. And it can get kind of complicated. But some of the gaps are relatively straightforward. You literally have a moon cruising through the disk. And so, for instance, this Keeler gap here, this is caused by this little guy called Daphnis, a relatively tiny moon that you can see there, sort of amazing, cruising through the disk. And the gravitational interactions not only clear path here, but also cause these neat structures. So we somewhat recently know now that there's also extra vertical height. So these are waves in the matter of the disk caused by the gravitational interaction of the moon with ice crystals in the disk. And to be clear, these shepherd moons, they're not plowing material out of the way. It's a gravitational interaction. So they're causing anything that would be in the way to get moved out of the way because of gravity. So it's not like a snowplow or something like that. So the next giant planet is Uranus. It's about twice as far from the sun as Saturn is from the sun. So we're getting extremely far out now, and because of that, the orbital period is very long, right? It's about a human lifetime if you're lucky. And it's much smaller than Saturn, but still quite large. Now, one thing that's very unique about Uranus is that its tilt is extreme. So, the Earth is 27 or 23 degrees from the ecliptic, and that's what causes our seasons. And Uranus is basically sideways. I mean, it's a little beyond sideways even. A 98-degree tilt, so that's pretty interesting, and gives some clues as to the formation of the solar system and what's happened to Uranus, and we'll talk about that in next week's lectures when we talk about the origin of the solar system. The composition is sort of similar in spirit to Jupiter and Saturn, but it's much icier. So there's not really this big gaseous envelope. It's pretty much just rock, ice, and this thinner, relatively speaking, layer of molecular hydrogen. So it's much more ice dominated, and Neptune's pretty much the same, and that's why you'll often see these referred to as ice giants rather than gas giants. And this is partly due to the fact that they're less massive, but also due to the fact that because they're less massive, they're a lot cooler. The really neat sort of cyan blue color that you see here is that's due to methane in the atmosphere, and you'll see some features like this. In this case, this is actually an aurora happening, like that happened at the North Pole of the Earth. So that's not a cloud you're looking at; that's an aurora. For the most part, when you look at Uranus, it's relatively featureless. The ring system is relatively complex, so it's the second most complex in the solar system. There's at least 27 moons, and there's really like kind of 4 major ones and 6 that are even worth mentioning. And you can see that the first 4 or so are relatively substantial in size, and then going down from there, they get a lot less massive and aren't particularly notable. Neptune is the last of the Jovian planets, extremely far from the sun, so 30 times the distance from the Earth to the sun, and because of that, the orbital period is huge, right? It's only gone through a few orbits since its discovery actually, and the days are, a little less than or a little more than half of an Earth day. This is so far away that it's really hard to see this. I mean, you needed advanced telescopes to actually um, image Neptune, and these beautiful pictures that you see of Neptune, they're actually made of a space probe that went out and got closer to take pictures. So far away that Neptune wasn't discovered by observing it like all of the other planets. Instead, astronomers were looking at Uranus's orbit, and they saw that it was perturbed in such a way that there should have been, and there must have been a large planet kind of near-ish by, and that was the prediction of Neptune, which is of course true. The size itself is not too different from Uranus, and again, it has a blue color because of methane in the atmosphere. The atmosphere, however, though, is much stormier, and it hosts the fastest winds in the solar system. So 2,000 kilometers per hour. Right, that's crazy fast. And this extreme weather also has sustained cyclones like you see on Jupiter. So you see things like the Great Dark Spot. As far as I'm aware, none of them are known to have sustained for like hundreds of years, like the Great Red Spot, but for several years these big cyclones can be sustained. The ring system here is also there, but relatively simple. We have 14 moons. You can see where they're distributed from Neptune here, and by far the largest is Triton. So that's the main one you would consider when you're thinking about moons of Neptune. So rounding out the discussion, or close to rounding out the discussion, moving beyond the planets, the next thing that we have is the Kuiper belt. And it used to be thought, the common understanding was that Pluto was the ninth planet, because this was the only object known to exist out in this region. And there was a bit of a crisis when more of these objects started being discovered. So on the horizontal axis here is the distance from the sun in astronomical units, right, Earth to sun distance. So there started to be more and more objects discovered, and then finally, okay, a definition was made. You have to clear your own orbital path. And clearly these objects have not. There's lots of stuff in the neighborhood. And so instead these all got demoted to things like called trans-Neptunian objects. This is lumped in with the Kuiper belt. All right, so what you have here are a handful of dwarf planets like Pluto and Eris, objects that are in hydrostatic equilibrium. They're spherical. They even have their own moons. And they're peppered in here with lots of smaller objects that are mostly icy in composition. Besides not clearing their own orbital path, one thing that really distinguishes these from the planets is that the eccentricity is rather high. So remember that's how elliptical an orbit is. So that's the vertical axis here. So many of these are quite eccentric. The orbits are not really circular at all. Some of them are extreme, like Sedna is a really eccentric orbit, and the inclination angle is also very high. So it's not shown on this plot, but many of these are not really in the ecliptic, which distinguishes them as well from our planets in our solar system. And some of these, can actually be imaged, and most of the rest of these are kind of artists' reconstructions. But again, many are large enough to be spherical and have their own moons. So you have these dwarf planets. Moving out to the outermost reaches of the solar system, the furthest stuff that's, you're talking about stuff that's kind of barely bound to the sun anymore gravitationally, and some of it essentially isn't, just a passing galaxy can kick stuff out. You get out to the OORT cloud. So to be clear, this is theoretical. This has not been observed, but I'll explain why in a moment, why we think it's there. So it's a mostly spherical distribution. There is a disk, but you're talking about something that's mostly spherical. These are icy planetesimals, and this is very far from the sun. So this little rectangle here, this is everything else we talked about. So all the planets, the Kuiper belt, right? And in the Kuiper belt, you were already hugely far from the sun. This is much further than that. So astronomical units are kind of silly to use anymore. You're at tens of thousands of astronomical units. So instead, let's talk about light years. So you're at like a tenth to a full light year away from the sun. For context, the closest star to our sun is 4 light years away. So this is pretty far away. The reason that we think that the Oort cloud exists is you see these comets that have extremely long periods. So we can tell that they have long periods based on the eccentricity of their orbit, and then also partly based on the historical records of ancient astronomers making records of objects. So you have these very long period objects, these comets. We know just doing relatively simple or straightforward gravitational modeling of these that they have unstable orbits. So if you have a comet that has a period of like 10,000 years or something like that, eventually it's either going to be ejected from the solar system or it's going to crash into the sun. And so that can't have existed for all eternity orbiting like that. Even if it could exist orbiting in it for the history of the universe in that way, or the history of the solar system in that way, the comets, right, they give off jets. They boil off when they get close to the sun, and eventually that causes them to break up. And so essentially these comets cannot have existed for the history of the solar system in these highly eccentric orbits. Instead, there needs to be some reservoir of icy stuff hanging out where occasionally gravitational perturbations will kick one of these objects from its safe orbit way out here into some highly eccentric orbit where it can then swoop by the sun, where we can see this really cool comet, and then fly way back out. And so that's why we believe the Oort cloud, more or less must be there. And the way that the size of the Oort cloud is hypothesized, besides some modeling of origins of the solar system, is based on comet properties. So you look at the eccentricity of the orbits, you look at the masses of the comets, and that's where we get these distances of the distance from the sun, and that's also where we believe the mass, or that's how the mass is derived. So about 5 Earth masses worth of ice. So kind of a lot of stuff out there. Again, I want to emphasize it has not been observed yet, but pretty sure that it kind of must be there just because of these long period comets. And that is it for this introduction to the Jovian planets for Astronomy 1000.